Hello, everybody. I would like to share with you my study about the magnetic field toward M17 clouds using dust polarization with SOFIA data. My name is Thường Hoàng. I'm from University of Science and Technology of Hanoi. Today, my talk will cover three main aspects of star formation: gravity, turbulence, and magnetic field. So, in summarize, this is the study of magnetic fields toward M17. So we aim to measure the B field in the plane of sky using the SOFIA data at 154 micrometers. You can see this is the white box in the SOFIA observation region. And in this study, we use the DCF techniques to estimate the strength of the B field in the plane of sky. And for the outpost, we measure a strong magnetic field. It's about microgauss in the lower and higher density regions. And we estimate the Mach number to know that the magnetic fields dominate turbulence. And this is realized in the well-analyzed magnetic field morphology. And we also estimate the subcritical values of mass to flux ratio. This could be the result of the low star formation rate in the M17. We also found evidence of the radioactive torque alignment and the disruption mechanism for the relationship between the polarization and the dust temperature. So first of all, to look at the data, and we apply the quality cut of the first one in the signal to noise of the intensity greater than 236. This is equivalent to the 0.6% of polarization errors. And the second threshold is the signal to noise of polarization greater than 3. And you can see in this map, the background map is the intensities, and the vector here are rotated 90 degrees to change the B field orientation. And the scale of the polarization is labeled here, and the beam size also labeled. And to estimate the magnetic fields in the plane of sky, we will use the DCF techniques. In this method, we know that it depends on the three main parameters: the sigma theta, sigma nu, the velocity dispersion, and the gas number density. We use the dust polarization data because this is the chaser of the magnetic field. So for the gas number densities, the first we divide the master mass after cut become two main regions: the upper mass and the lower, as the and we assume the physical volume of molecular, and that's why we can draw ellipse here, and we can calculate the radius of the ellipse about 69 arcsecond for the upper region, and for the lower it's about 120. And after that we estimate the number density. You can find the techniques from this reference. And after that, we are going to estimate the dust polarization angle dispersion. This is the theta mass of the SOFIA. For this angle dispersion, we use the structure function. This is basically the 2-point correlation function. In this function, we consider the number of pair, which is NL here, and let's consider a pixel as a defined location, and then we consider all the pixels within a circle with the radius of L, and then we take the difference. And when we express the structure function using a Taylor expansion, we know that it can approximately with two parameters A and B. A for the larger scale variance of the B fields, and B is the contribution of the turbulence to the B fields. And here is the structure function of different maps, the master, the upper, the lower. And you see I fit the structure function with a model of the Taylor expansion. And we found at the distance equal 0 here, the cross section is the value of B. We can see B about 14 here, and then we know that the angle dispersion sigma theta is equal to B divided for square root of 2, and we found it's about 9.96. And for the fitted model like this, we fit for a distance of 8 pixels, which is equivalent to the 2 beam size. And the next one, the last parameter needs to estimate is the velocity dispersion. For this one, we use the 13 CO data cube from Noble-Gamma 45 mesh telescope. And we can see the figure on the top left here is the intensity map. And this intensity, we know that there is a core with a very high intensity here. And then this region have the same velocity. We can see that in the velocity map. And we can actually predict it's about around this 20 kilometers per second, and there should have another velocity map here. It should be in the order of the 30. To estimate accuracy, the velocity, we integrate over the velocity from minus 20 to 60, and we feed the data to the model, and we know that the fitted values give us the average velocity map peak at about 20 kilometers per second. And we measure the non-thermal velocity dispersion about 2.3 kilometers per second. So when we have three parameters, we are going to estimate the B-field strength, and we found for the upper maps, the values about 327 microgauss. For the lower is about 839, and we know that this is a strong magnetic field. This could support the counteract of the gravitational collapse. And from the B field in the plane of sky, we going to estimate the Mach number, and we found the value of the Mach number is very small compared to 1, and we can see that the morphology map is very well aligned. We see here in the envelope it's very well aligned, and then when the field going into the core, we see the a little bit random here, and for the upper map, it's in the outer flow of a source in the north, and we also estimate the mass to flood ratio. We found the value is smaller than 1, and this could explain the low star formation rate in the M17. And for the reroutes of the B field in the plane of sky, we see is compatible with previous studies like Brogan using the Riemann effect, and Pelli estimate a strong magnetic field peaking at about 600 microgauss. And furthermore, we going to see the relationship between the polarization and the first one is the intensities. And we see that the polarization decrease with the increasing of the intensity. For the map at the middle is the relationship between the polarization and the column densities, and we see overall the P decrease when moving from a lower density to a higher density gas. And it's interesting to notice that the relationship between the polarization P and the dust temperature T at the lower region because of the irregular grain alignment. And then when the temperature increase, the dust polarization will increase. This is the evidence of the radiative torques. And for upper mass, with the high dust temperatures, it induces the very fast rotation of dust, and it can disruption the dust grains, and it lead to the decrease of the dust polarization with the T dust. This is the summary of my talk. We estimate a strong magnetic field in M17 using SOFIA 154 micromass. The max number, the subcritical value of mass to flux ratio, and we found the evidence of the RAS alignment. Thank you.